We're going to pick up where we left off with alkenes and alkynes. Most of this video will deal with alkenes. So where we left off was that alkenes are trigonoplanar in geometry, meaning all of these angles are 3 parts of a circle, 120 degrees, while alkenes are linear in geometry, and so meaning these angles are 180 degrees. So it's important to remember those geometries. The other thing is that carbon-carbon double and triple bonds are much more reactive than carbon-carbon single bonds. And we're going to delve into that reactivity in this chapter. Moving down. So alkenes, like substituents on rings, can have cis-trans isomerism. In other words, they can exist as different compounds. One is cis, one is trans, and they're different. They're isomers. So if you recall, in rings, the same holds true where if one substituent is up and the other one down, it's trans. And if they're both pointing in the same direction, they are cis. With double bonds, it's different. Except for the concept that opposite sides are trans and the same sides are cis. So in an alkene like this, where the 2 methyl groups are on opposite sides, we would call this trans. And there's another version of this molecule in which the 2 methyl groups are on the same side, which is cis. Opposite sides, same side. So you cannot convert from one to the other than by doing a chemical reaction. So, and the important reason for this is that you cannot rotate around a double bond. A double bond is fixed. And you can convince yourself of this by building the model. Because when you build the model, you end up with 2 bonds and try and rotate it. Well, don't try too hard because then you'll break your model set. But you'll see that it can't rotate. You'll also see that these molecules are flat and trigonoplanar in geometry. Cis and trans need to be part of the names because they represent different compounds. If someone was to come up and say, can I have 1, 2, 3, 4? Can I have 2-butene, which is the name of this compound? You would have to ask them to specify whether they want cis 2-butene or trans 2-butene because they're different. So those cis and trans have to be part of the names. I'll go into some simple naming of alkenes, and as I pointed out on the homework sheet posted on Canvas, that the chapter really does harp on naming quite a bit. But and while that's important to be able to converse, to understand the kinds of questions and problems that can be asked and answered, the naming itself is not really that important. It's only a means to getting to talk about the subject matter at hand, which is much more interesting. For example, structure and bonding, and above all, reactivity or activity. So we can do some simple examples though. And I'll point some features out. You want to give the alkene the lowest possible number. So 1, 2, 3, 4, 5, 6, rather than numbering it from this direction. That would be 1, 2, 3, 4. It would give the alkene a 4 number right there, which we don't want because now we have a 2 number. So you're aiming for the lowest possible numbers. So we would call this 2, and it's a 1, 2, 3, 4, 5, 6 hex. So these stay the same. Ene. So not hexane, but hexene. So alkenes end in the ene substituent. Suffix. This has 1, 2, 3, 4, 5, 6. So it's also a hexene. However, it's got 2 enes. So we throw in hexa di for 2 ene. It's a diene if it has 2 enes. If it had 3 enes, it would be a triene. If it had 4 enes, it would be a tetraene, pentaene, hexaene, and so forth. Until you get to so many double bonds that they just call it a polyene, actually. So I think we've given the 2 enes the lowest possible numbers, starting at 2 and 4. And notice you name the alkene with the number of the carbon where it starts, and you number through the alkene. So that's sort of one of the things to remember. Number through the alkene. It's pretty much common sense once you start doing these problems. All right, we determined this is a hexadiene. It's a 2,4 hexadiene. Notice what I left out in both of these names. The above is trans. The below is trans. This leads into the next problem. So here I gave the names and we want to try to draw the structures. Trans cis 2,4 hexadiene. Oh, I just wrote that. Okay, we just did that one. So let's do the cis trans 2,4 hexadiene. That was my intention, I believe. So 1, 2, 3, 4. This is now cis. 5. Here's our other double bond. This one is trans, and that's our 6. So I'll redraw it a little nicer. 1, 2, 3, 4, 5, 6, 2, 4, cis trans 2,4 hexadiene. So that's that. What about this one here? 1. No, we don't want to start numbering there 1, right? Because that would give these alkenes numbers of 1, 2, 3, 4, 4, and 6 rather than the other direction. So 1, 2, 3, 4, 5, 6, 7, 8. So this is a 2,4-diene. It's an octene. So it's an octadiene. They throw the A in there to help, I think, the way you just saying it. Rather than octadiene, you say octadiene. It rolls off the tongue a little bit easier, I think. So it's a 2,4 octadiene. And the 2 alkene is cis, and the 4 is trans. If you ever have trouble seeing it, you can draw in the implied hydrogens. It's clearly trans, clearly cis. So the cis goes along with the 2. You just put them in order. Cis, trans, 2,4 octadiene. And now we have a cyclo compound, just like in the last chapter. So this is a cyclo. If it was no alkene, it would be a cyclopentane. So instead now it's a cyclopentene. I always draw the parent, write the parent name first. That's like the parent name of the compound. Then you look at what's stuck on or other things. So numbering through the alkene, like I said above, 1, 2, 3, and we see that there's an isopropyl group on there. So we can't forget what we learned before. That's the name of a common substituent. An alkyl group, an isopropyl group. It's 3-isopropyl cyclopentene. And notice I didn't number it through the alkene in the other direction. 1, 2, 3, 4, 5, because that would have put the isopropyl group at 5 instead of 3, and 3 is preferred. All right. Wanted to get to the beginning of this next topic, which I'll continue for sure in the in-person class this week, showing some more of the subtleties of these. But alkenes undergo addition reactions, meaning the alkene adds things to both carbons of the alkene, while at the same time the double bond goes away and is replaced by a single bond. That's not really what's happening. It's the fact that the double bond itself is reacting in each case. The double bond, as you saw in the last video stuff, has a different structure. Remember, these two lines don't represent the same thing. The double bond has electron density above and below the plane of the molecule. It's sort of sticking out there. It's a region of high electron density, and so therefore it's reactive and can form bonds. So these first 3, I'm asking you to commit to memory. They're pretty easy to spot what's going on. The alkene in hydrogenation, adding hydrogen, adding 2 hydrogen atoms, or a hydrogen molecule. The net reaction, notice what happened here. You added a hydrogen to each of the carbons of the alkene, and the double bond is gone. Essentially, the covalent bonds here to hydrogen have obtained electrons from what was the double bond. So that's hydrogenation, addition of hydrogen. You just want to remember these conditions along with reacting with an alkene. An alkene can add, in the same way, a bromine molecule or bromine atoms to each carbon of the alkene. Notice the double bond is gone. So the most common mistake is to do this, to forget to remove the double bond. And what happens there is in each carbon you get 5 bonds. So very wrong. We call them Texas carbons because of the Lone Star of Texas. 5 points. Not that people in Texas do make this mistake more than anyone else. You can add water across a double bond. Again, double bond's gone. You've added H2O in the presence of an acid catalyst. This is sulfuric acid. And that helps the reaction along and adds water across the double bond, being HOH, H2O, right? Hydration, like being hydrated. So we have hydrogenation, bromination, hydration. Our fourth reaction, the net result is that you add a hydrogen and either a bromine or a chlorine across the double bond. The double bond goes away. All right, so you want to remember that just like the other 3 above. I chose to do this reaction mechanism in depth. So reaction mechanisms. How does the reaction work? It's really not appropriate to have a class in organic chemistry without realizing that organic chemists need to understand mechanisms, how things work, in order to create new reactions, to invent new things, or to simply to understand what might happen if you put 2 things together. Will it explode? Will it do nothing? Will it do what you want it to do? and to what extent. So, our responsibility in covering the science of organic chemistry is to delve a little bit into mechanisms. And I'm going to do this very quickly and go into a lot more of this in the next videos or in the next in-person class. Electron pushing arrows. Many people are surprised that reactions in organic chemistry are almost entirely governed by the movement of electrons. Electrons, the things that orbit atoms. Pairs of electrons typically move to form and break covalent bonds, which is just two electrons being shared, right? That's where we draw every one of these single bond lines or double bonds or triple bond lines are covalent bonds. They often move in a sequence of moves, like sort of all at the same time or one after another. These are key concepts. So if you have two electrons contained in a bond, you would represent their movement by this arrow like that. Both of those electrons might be moving to form a new bond, and in the process breaking this bond that existed before. Lone pair electrons can move to form bonds. Some of what governs these reactions are the fact that some bonds between atoms are polarized, and we're going to indicate minus and plus polarized atoms with the Greek letter delta. So carbon to bromine, for example, is a polarized bond where the carbon has a partial positive charge and the bromine has a negative partial charge, not a full charge. So partial charges exist in polarized bonds like this, and it's due to electronegativity. Bromine is electronegative. We're going to revisit these concepts over and over again until we get them down really solid. We can break down the steps in the reaction I just showed above in this way, in a two-step sequence. So I said electrons move in sequence of events. The two electrons of the double bond in this alkene will form a bond. This bond will break. That bond breaks, forms a bond, a new bond, to that hydrogen. These electrons in this bond break and go up onto the bromine atom. The HBr is polarized. So it makes sense that negatively charged electrons will go toward a positively or partially positive hydrogen. And they go in this sequence. Bond forms, bond breaks. Technically, this bond is also breaking. That's not an arrow. That leads to this structure, which now has a new bond. There's a new bond to carbon from this carbon to the hydrogen. That leaves this carbon right here without a bond that it used to have. So now it only has 3 bonds, and check this out. A carbon with 3 bonds is lacking electrons and has a plus charge. So this carbon, if you look at the electrons right near it, it has 3 electrons, whereas before that same carbon had 1, 2, 3, 4 electrons right surrounding it. So this is short electrons. That has a plus charge. Thus the next step. This next step is that a bromine by itself has extra electrons and a negative charge. How did it get the extra electrons? Oh yeah, back here, over here, those electrons went up onto the bromine. Technically, this bromine has 4 lone pairs on it, while before it had only 3 and a bond to hydrogen. So this has extra electrons. That makes it minus. One of these pairs of electrons can go and form a bond directly to that carbon. Minus to plus. Makes sense. Forms a bond And this right here is the bond that it just formed. So now we see the net reaction, addition of HBr to the alkene. We're going to go through this enough times that it becomes second nature. The other three reactions above, we're going to hold off and just sort of memorize that that's the result of those reaction conditions. This is going to be used as our example of learning and understanding reaction mechanisms in organic chemistry. A first reaction. All right. A little bit longer video than usual, but some important stuff. Big chapter.